Thank you for coming to my talk. We have a lot of interesting stuff to talk about. So we're just gonna get into it. So we know why we're here. We are here to solve the Rubik's Cube using group theory and functional programming. In particular on our agenda, so we're gonna learn a little bit about the group type class and permutations. So the group type class actually already exists in your functional programming library. So CATS, for example, has a group implementation. Notably, it doesn't have a dedicated documentation page though. So perhaps you can bridge some of that gap here. We're going to use a simple permutation class that I've written up for this. And we're going to see how theory informs the modeling and design of a DSL and solution. And finally, we're going to combine all this theory to solve the Rubik's Cube. And we're going to solve it live on screen with this Bluetooth Rubik's Cube. So I have it enabled here, where it'll track all the moves that I do here, and that'll be useful throughout the presentation for demonstrations, and we'll get back to that. Okay, so let's start with a definition of a group. And in fact, as a recap, you've heard of what a monoid is, probably. A monoid just has an empty and a combining operation. So the empty is your identity element. And here's a monoid for ints. It's a typical example. You have 0 and you have addition. So you can add ints with a monoid. Now here is a definition of a group. This is the abstract definition. The group is just like a monoid, except that it has here the inverse. So for ints, that means negation. So now we have negative numbers, and you can combine negative numbers to get back the identity. Now, this is an example using the integers, but I actually don't like this example. So this is a common example. I don't like it. It doesn't tell you the full story of what a group actually is and what you can do with it. So, for example, with a monoid, that tells you that this is foldable. We can do MapReduce, we can optimize in various ways, by doing like parallel computation and removing intermediate data structures. And you could imagine with the group, like perhaps you can also take the inverses and collapse them and avoid those computations. But there's a lot more to it, which is why we're going to show you a particular kind of group called a permutation. So this is a perm, and we're going to go into a demo here. Let's bring up a worksheet. In fact, actually, we'll bring up a REPL. So we know what permutations are. They're scramblings, right? So if we take ABC, permutations in Scala, then we can do like for each print line, and we get all these scramblings of ABC. Similarly, we could do that with 1, 2, 3. And there's a similarity here I want to point out is that, okay, the first line of these two is the same, it's just in order. The second line here is a swapping of the second two elements. So what a perm does, is it encodes that. So this is that swapping of the second two elements. You swap 3 with 2. Swap, and this A here is just swapping 1 with 2. Okay, so what can you do with these permutations? These perms are not just data structures; they are functions. So we can apply these to numbers. So A applied to 2, that gets us 1. B applied to 3, that gets us 2. Okay, so these are functions, and as with your regular functions, you can compose them. So if we compose A times B, and we apply that to 3, we get 1. And I'm going to do just a few examples here of some multiplication of two perms. So we have A times B, and normally with functions you don't get a data structure back, right? But since these are represented as data, we do actually have a physical thing. So we can compare that. We can compare that with equals perm 1, 3. Okay, so a few more of these. B times A. We can do B times B. And we have many more permutations. And now what I want to point out here is that just by multiplying A and B, we have all these permutations: 1, 2, 1, 3, 2, 1, 3, 2, 3, 1, 2, 3. These are exactly these numbers here. So we have all 6 of those. So yes, perms form a group. There's a composition. I should show you the inverse. So if we multiplied A by itself, we get the identity, right? So A is actually its own inverse, A dot inverse, and then B dot inverse is just like B times B. So this fits the definition of a group. But one reason I want to point that out is because, oh, 1 second here. Okay, so these 6 elements here, these are the actual group. It's a group of 6 elements, and you can generate completely by multiplying just 2 elements of a group. So just like how with the Rubik's Cube, you have these 6 operations which are face turns. When you start combining those operations, you get the full list of 43 quintillion possible states of the Rubik's Cube. But there's more to it than that. So we have, yes, this is a group. In particular, I want to note, so this is a group definition. I want to note that because all these elements are actually functions, well, all of these are actually bijection. So bijection is exactly the same thing as a scramble, as a permutation, right? And it turns out that for any kind of group you get, so you have A, you can define a function using A's operation like this, and you can define an inverse function G. So not just for permutations, but for any permutation, for any group, all the elements are bijections. So if all the elements are bijections, all the elements are also permutations. And this is essentially what Cayley's theorem is. And we can do a more formal proof later. But the point is that any group you can define can also be defined in terms of permutations. And with permutations, we have all these useful operations. We can for example, we can compose 1, 2, 2, 3, 3, 3, 4, and this gets us the 4 cycle 1, 2, 3, 4. We could also take 1, 2, 3, 4, and we could decompose it into individual transpositions. So that would be true for anything with a group structure, right? You can represent it as permutations. You can build up your actions. You can and you can decompose them. And if it's easier, you can represent in terms of permutations, which are a familiar object. Okay, how are we on time? 10 minutes. Cool. Okay, and this is just a recap of everything I've said. We can represent our functions of data. We can leverage centuries of group theory knowledge and theorems that have come out, and permutations are computationally useful. So that's why we're using permutations. In fact, any group is a permutation. Okay, so now we'll look into the Rubik's Cube. So the Rubik's Cube, naively, you can think of this as a permutation of the stickers. So it sort of makes sense to represent as a permutation, but there is more to it than that. Let me pull this up. It has some structure, some rules that we can encode into group theory. So for one, there are, let me pull up an image for you here. There are 2 types of pieces here. So we have corner pieces and edge pieces. So these three stickers on like that red, green, white corner, they can't ever be moved away from each other. And since these piece types are distinct, a single corner can only ever be moved to the location of another corner. So demonstrating that with the cube, say this is red, green, white. If I did a clockwise turn of the red face, it is now in the back position, right? So we can think of this as having two permutations within it, a permutation of 8 corners and a permutation of the 12 edge pieces, right? So if we ignore just the edge pieces, then we have a smaller puzzle. It would be the 2x2 Rubik's Cube. And it turns out this is something called a subgroup, right? So this is composed of at least 2 subgroups where you have the corners only puzzle and the edges only puzzle. And then it also has orientation. So this red, green, white piece, I could do a transformation here, and now we have the same piece in the same location. So that's its orientations, and the orientations also form a subgroup. And these are particular kinds of subgroups. These are normal subgroups, which means we can. It's easy to work on them individually. So we can solve these individual puzzles first when we're trying to solve the larger puzzle. Okay. A note about this. So this face turn, it is a pairing of 2 4 cycles. You have a 4 cycle on the edges, 4 cycle on the corners. Now, I mentioned earlier that you can decompose a cycle into pairs, right? So a 4 cycle is composed of 3 pairs, which is an odd number of pairs. And it turns out every permutation can only be composed of either an even number or an odd number of pairs. So that's relevant for solving this Rubik's Cube because we'll always have the same parity on both our corner puzzle and the edge puzzle. And we'll get back to the idea of parity later, but you should just know about it for now. Okay, so here's my model of another Rubik's Cube. Like naively, you might have just made this like an array of 54 elements. But here we're going to model it in pieces. So the whole cube state is composed of both the corners and the edges. The corner state is composed of its permutation and the orientation of those corners, similarly for the edges. And in fact, the orientations can also be represented as groups, or that each corner orientation, for example, is just the group generated by like a 3 cycle. And this is what our group definition looks like for cube state. So when we're combining 2 cube states, which is to say, doing a set of moves that creates one state and then following that with another set of moves, then we combine it by just multiplying the states of both groups. So we multiply the corners of both groups and then the edges of both groups. Similarly, the inverse is just the inverse of both groups pairwise. And you can this type of group composition is called a direct product. So you could generally take any 2 groups and concatenate them in the same way. This could be part of the group the group type class interface that just allows you to combine 2 groups into a larger group, and that's called the group product. And there are technicalities I'm hiding there, but we can say that for a Q&A. The corner group is similarly, it's just you combine the corners and you combine the orientation. It's actually a little bit more complicated here because in this case, we are taking, this is what's called the subdirect product. And you could come to that intuitively, or you could use theory. In this case, I'm sort of just giving it to you because there's not much time to go over that. And then similarly, even the corners are groups that you combine. So So yeah, our definition of a group for a cube is just composed of definitions of groups all the way down to the orientation of a single piece. It's just subgroups all the way down. So how might we start using all this information to develop a solution? And how we are 15 minutes in. Oh, this is great. We'll have plenty of time. Okay, so the first concept I want to teach you about is commutators. So I'm going to bring up a REPL here, and I'm going to bring up two particular permutations here. This cycles the first 5 elements, and this cycles 5 through 9. So these two permutations intersect at only a single point. Now, where a commutator gets useful is that if you were to do so a commutator is an expression of the form A, B, and then A inverse, and then B inverse. So if we were to do that with this times P dot inverse times Q dot inverse, what we get is a three cycle of elements, 1, 6, 5, which is to say that because these two perms hardly overlap, most of these operations in PQ, in the commutator get canceled out. And that's something I neglected to point out earlier. Groups aren't necessarily commutative, right? So with integers, you can add and subtract in any order you want, and you can swap those around. But it's not always true that PQ, P inverse, Q inverse is back to the identity. So with a group like the Rubik's Cube or permutations in general, you have to do your operations in terms of operations like this here. Okay, so those are commutators. All right, let's talk a little bit more about parity. So all these perms, let's take all these perms are either even or odd, right? So it turns out when we have an even permutation, we can take each of those, we can take those transpositions and we can take them in pairs. And when you multiply two transpositions, you can get a 3 cycle. So that means a perm like P, which this is an even permutation, we can decompose that as 3 cycles. So P can be decomposed into 1, 4, 5, 1, 2, 3. And that helps us manage these larger permutations we're getting on the cube. We can decompose it into 3 cycles, and since a commutator can help us solve these 3 cycles, that helps us solve the problem in general. And a final note, the other tool in our box here is conjugates. So this is an expression of the form A, B, A inverse. And conjugates are useful when you have like a normal subgroup. Excuse me. So let's say our operations, so back in the slide, this B is one of our commutators. It's a 3 cycle. So those 3 cycles form a normal subgroup, which is to say, the permutations of the cube are a normal subgroup. And we can use and when that's the case, a conjugate of that operation is also the same type of also stays within the same subgroup. So a conjugate of a 3 cycle and any corner permutation is still going to be a corner permutation. And just to demonstrate that, so here we have on screen, let's say we had, a useful element. What I'm going to do here is, well, before we get into that, let's just show an example of a useful operation. So we can do we'll do a commutator. So here we've swapped this front right corner and this back right corner. We've left the front intact, but the back has been messed up somewhat. So we can do a B move, which intersects at only that one point. So this only affects the front face and that one corner that was affected as part of the previous algorithm. Then we can undo the first move and then undo that front move. And now we have a 3 cycle, right? But what if we didn't want to cycle those 3? Then we could take another element altogether and put it in the place of one of those. So where that move I just did swaps these top 3, if I were to do a half turn on the back, I can swap these 3 instead. And that's essentially what a conjugate is, right? It lets you get more mileage out of that single commutator you'd invented. All right. And now we get kind of into a demonstration of solving some of these. So we'll pull up the worksheet. Okay, here I've encoded a scramble. And we can print its state. Here, we see the corner state, the edge state, the permutations and orientations. But in particular, we don't have time for kind of a full-on solution. So we're gonna look at just the corner permutation. And when we do the scramble, the permutations of the corner, this is what we're doing to the corners. We don't need to, and we can solve this independently of everything else. So remember that actually I showed you a different commutator, but here's another commutator for cycling corners, right? It gives us some algorithm. We can print that in a nice way. So we can do simple comm that turns. Okay, so this is the algorithm for that commutator that generates. But like I said earlier, we can conjugate that to invent new algorithms, new commutators. So this one here that we just did corresponds to the permutation 187, right? But if we were to change something, let's say conjugate by U, which is a turn on the upper face, now we get 487, right? We can create many different variations of that. Let's say this D became a D2, D2. We get yet another algorithm. So we can take our commutator and kind of break it down, and we could insert variations here. So instead of U, I could have done U2, or I could have done U3. Instead of R2, I could have done L2. But you'll note here, this list, maybe I can't do all of those. Okay, we'll just do conjugates here. So we have a list of one possible algorithm. But if we start to do U and U2 and U3 down here, then now we have 4. We can do D, D2, D3, and we're getting more and more algorithms. And this is growing fairly quickly, but remember, we only need 56 different cycles. So it doesn't take much modification before we get 56 distinct cycles. So going back to our scramble, it was that one permutation 1486325, right? So we can take that scramble, that state, that we can take the corners, and then we can get just the 3 cycles from that. So we're just gonna get like a pretty print that, and we'll print that. Actually, this is not exactly honest here, because what we want is kind of what we want is the inverse of the scrambling permutation. So we take solution cycles, that inverse, and then well, actually we take the scramble and then we invert that. So we can take the corner permutations and get the inverse. We'll just print that as a. And this tells us that in order to solve this scramble for the corners, we first have to do 184, then 136, and then 152. Okay, so I don't have time to code up like the full full generation of all possible commutators, but you get the point. You can search for these commutators essentially by looking for algorithms that intersect at only one point, and then you can make variations of any commutator you discover by just doing conjugations. Okay, so I've actually already coded this up here. So if we run this, here is an example scramble, and let me pull that up next to. Okay, we're going to pull that up, and then we're going to pull up our code, our worksheet. We actually want our terminal. Okay, here. Okay, so I'm going to. We have 3 minutes. That's plenty of time to solve Rubik's Cube. Okay, so here we have a scramble. This is the permutation it generates. This is the orientation it generates. The scramble is actually just a corners only scramble. We're going to ignore edges for now, but you solve them in basically the same way. So we're going to do the scramble, D2 U R2 D2 U prime B2 R2 B2 R D prime B2 D B2 R B2. And it looks like I didn't mess that up. Okay, so what we have here now, this here describes that permutation. And this here is our solution. So if we first did 163 and then we did 157, we'd solve the permutation. Now I didn't show the generation of like a orientation commutators, but I can just solve that independently here. Okay, so we'll fix the orientation. Okay, so the orientation is fixed, and oddly, interesting. So the Bluetooth web app is out of sync with my Rubik's Cube, so I can't show this right now. Okay, what I'm going to do, basically, I'm going to execute these 2 algorithms, and now we have to use my camera because that's out of sync. But we can do this one here. So it's like a L2 D prime L2, U2, and oh, whoops. Okay, so we have L2 D prime L2, L2, and we have B2, L2 D prime, L2 D, L2, U2. And as you can see on my cube here, there's only a 3 cycle left. Everything else is solved. So now I can just solve the second cycle, and now we have what do we have? And there we go. So the Rubik's Cube is solved. And if everything had gone according to plan, this cube here would also be solved, but they're out of sync for whatever reason, and I can debug that later. But it works, and I'm happy about that. And you could be happy about it too if you want. But the key takeaways here are that groups aren't just a monoid with an inverse. They are about space transformations. They allow us to turn our functions into data, which we can then manipulate. So we can manipulate our functions in that way. So that they're great for computation. And when our intuition fails, we can rely on the centuries of group theory that of all the theorems that have been developed, and look into the literature and use that and leverage all of that knowledge. So groups are useful and not just fun and interesting. And perhaps next time you reach for a monoid, you should also look at, hey, is my thing a group? Okay, so that's my presentation. Thanks for watching. If you want to see more of this, I'll be streaming live with this library, doing more development, interesting stuff with it at twitch.tv/Stu2Squared. You can see my group, my code at this link. Of course, you can contact me on Twitter or email, or you can just DM me on Discord. That works too. But that's it. Thanks, everyone.